Welcome to Expert Answers with Jim, and I am Jim. So last semester, a student asked a question about a steel tank that is 10 meters tall with a diameter of 5 meters, in which somehow the tangential stress was measured in the material to be 80 million pascals. Based on the tank being full of water, the student was asked to determine the thickness of the tank. So this is a classical type of problem that you'll find on a strength of materials test or the fundamentals of engineering. And so it's an important one to know about. And so when we're talking about tangential stress, another word for it is hoop stress. That is the stress that comes from the internal fluid pressure wanting to bow out the material at any given station. So we can determine what that hoop stress looks like, and the way it is determined is it's coming from, again, the internal pressure from the fluid, and the material is resisting that pressure with this tangential or hoop stress. By looking at the static equilibrium of a section of the tank, we can determine the equation for tangential stress, and it is developed in almost every mechanics of materials text as the tangential stress is equal to the pressure times the radius of the tank divided by the thickness of the tank. Or another way, pressure times the diameter of the tank divided by 2 times the thickness of the tank, which will suit us a little bit better. And so we can solve this equation for the thickness of the tank if we knew the pressure, the diameter, and the hoop stress or tangential stress. We can figure out what the thickness of the tank should be. Well, the problem gave us the diameter. It gave us a measured tangential stress. It did not give us the pressure, okay? But it told us what the material inside the tank was, and it is water. And so if we look at water, what we'll see is the pressure starts out at roughly the atmospheric pressure, and it builds as we go down. In this gauge pressure at the bottom will equal to the density of the water times G times the height of the water. That is the change in pressure from the top of a fluid stack to the bottom. And this is the hydrostatic pressure equation. So we throw that into our equation. We have the density of water times G times the height of the water times the diameter of the tank divided by 2 times the tangential stress, and that will give us the thickness of the tank. And so at this point, it's all plug and chug. The density of water is 1,000 kilograms per cubic meter. The acceleration of gravity is 9.81 meters per second squared. The height of the tank is given to us as 10 meters. The diameter of the tank is given to us as 5 meters. And then finally, we were given the tangential stress in the tank, which we're assuming is at the bottom of the tank, as 80 million pascals. And Pascal, just to remind you, is a Newton per square meter. It's a unit of pressure. And so if we make note that 1 Newton of force is equal to 1 kilogram of mass accelerated at 1 meter per second squared, we will see that all these units come out to meters in the end. And plugging in the numbers, we end up with the thickness of the tank needing to be 0.003 meters or 3 millimeters, which is pretty thin for a tank that size. I thank you for your attention.